Now it comes to a little more advanced stuff, the facial recognition. So it would be great, just to present instead of using fingerprints to identify people, just put your face there and have the computer identify it. Easy, quick. I mean, if it can be done easily and quickly, why in the world are we wasting our time with making sure our signature is there, or typing in a new code for every place we're in, every place of business that requires a new code to get in. You need a code for your email. You need a code to get into your computer. All that stuff. If you just put your face in front of the computer and your computer will recognize your face, you don't need a code. So it would save a lot of work. It would be a great idea. If it works, it will be great for also crime, because if a person is seen on a video, and there are plenty of videos out there, all kinds of stores have videos of who's walking in front of it. I mean, if it's in public, you're allowed to take videos of it so far. So pretty much, if you've ever walked around the city, you can pretty much guarantee you've got videos of yourself and of your face, in who knows how many stores, at least in their files. And as far as we know, the government has been taking all this data, so they know what your face is. Anyway, so everybody has pretty much had their picture taken or have had videos taken of them. And wouldn't it be great to if we have a video of a criminal, as he runs out of the house they burglarized, and we'll say, well, we'll just take a look at all this video that's going on in the city. We'll know exactly where he is. Just match one video to another. If we have the facial recognition, we can, in theory, do that and find this criminal in any crowd that he can ever disappear into. So, in theory, it's a good idea. It's still creepy knowing that every one of us has data that anyone else can recognize if they have good facial recognition programs. But right now, there are many problems with this. It's still for the future. We actually thought we could do this, but because in the case of the Boston Marathon bomber, we were pretty sure, hey, we have plenty of videos. We'll catch these guys, no problem. It failed utterly. So it's not as simple as we might think. So how does it work? So the first thing you need is a clear digital photograph, which kind of eliminates all those videos that have been taken of you as you walk in public and pass by stores that want to have videos of whatever is walking in front of them for security purposes. So you need a clear digital photograph. We didn't know this at the time. We thought, oh yeah, don't worry, any video still will work. It is actually not true. We know we need a clear digital photograph. Very often we need a full face one, and not when the face is at an angle. There is some technology that can do it now without that. We'll see a little bit more about that later. So you need let's get a clear digital photograph. Let's start with that. The location of the cheekbones, mouth edges, chin, eyebrow ridges, jaw shape, distances between eyes and nose center, many other prominent areas, and the distances between them are identified and tabulated. So this gives you, and they're different for every person, and these are a bunch of numbers and let's say, it's digital data, which can be stored and put in a database and identified later. Now, the fact is that disguises will fool us. And I think there was actually a place, I forgot where it was. I think it was in Chicago, but I'm not sure. In one of the airports, in one of the parts of the airports, they were mentioned that they were going to put, these cameras there that were going to use for facial recognition. People started wearing masks in that airport. And they gave it up after a while. They realized it just didn't work. Getting these videos, it just wasn't good enough. Anyway, but disguises will or can certainly fool facial recognition software. Now, the more advanced ones won't get fooled, but unless the disguise is a little bit heavy, they have enough hair that falls in the right place will confuse it. Anyway, so it can be fooled. The facial recognition software that we have now can be fooled. Anyway, so first you get the digital photograph. You digitize all this information with distances and numbers, and after the picture is normalized. You have to make sure that the lighting is going to be the same. Remember, you're comparing this to a suspected photograph, let's say. And you want to have all these pictures on file. You want to have them all with the same lighting so that we can take this suspected picture, the suspect's picture or some suspected picture, and make sure that the background of that picture will match the background of all the pictures that are in the database. Otherwise, this can cause some problems because they may think that we found like the ear or the jaw shape, but really it was too light when you compare it to the other one. The other one was too dark. You have problems like this. You also have to make sure the picture is centered, so you can overlay one picture on another and get the data from that, and make sure the size is scaled correctly. So that's what it means. The normalized. It's put into the picture is put into a standardized size and lighting and other things, so that other pictures can be put into the same sizing, so you can compare them better. So that's what normalization is. Put it into a uniform framework, a standardized size and light background. So any other picture that that has a suspect in it, or it's suspected for whatever reason, you can compare it to the one on file. Okay, the most difficult part is to actually get the information from the picture and get it in a way that you can compare to others and in a way that can be clearly seen to be unique. Now, if it's a very good frontal picture, this can be done. And there are programs that will actually extract this kind of data. They are not simple ones. We can't go into them in depth because they are very complicated in the theories that make them work. Just the basic idea behind them. There are three general ways. The principal component analysis, they call PCA. What they do is they take the suspect picture, we'll call it that. We overlap it with after normalizing it, we overlap it with all the images that are on file. See where there are differences, and we score the differences. Say, let's say the eye different distance is let's say 2 inches too close. Then we say, oh, that's way too much. That just receives a score of, let's say, 0. Nah, this is probably definitely not a match. If it's, let's say, a third of an inch away, well, that's a little bit. The score is not 100 because it's not perfect. But it still might be the same person. It might have been a little bit of a glitch there that might have made it so a little bit off. And they do this with all the numerical data, the distances between the eyes, the left eye and the nose, the jawline distance, whatever it is. You still need a full frontal facial picture to get this done. That's one method of overlapping the images. There's also this linear discriminant analysis. Again, we're not going to go into that too much. The faces are given a vector, meaning the compared distances between them are given numerical values in the form of vectors. Vector is a mathematical construct. We will not be dealing with that. Just, again, it's all numbers here. We're not overlaying one face on another and comparing the pixels. We're talking about the information in the form of what the information is, how the parts relate to the others in the form of mathematical vectors. So we compare the vectors of the suspect picture to the vectors in the database, and the pictures in the database, and the results will show a match or a close match or not, and you'll be able to identify the person. In theory, we can pick one person out of the entire database. Here too, you need a full frontal facial picture. They are